Okay, hello everyone. Thank you for joining today. I'm going to go ahead and start my presentation here on my paper topic titled Evaluation of Optical Arrangements and Power Consumption for UV LED System Designs and Standard Draw Tower Configuration. So real quick intro on the authors. So my name is Ruben Monicum. I am the product manager for optical fiber products here at Horace Noble America. My colleagues, Dr. Darren Linhart and Kurt Harper, are also authors and contributors to the work that I will be discussing here today. So to begin with, I want to give everyone a background on optical fiber because this topic in particular is relevant for the content that I'm presenting today and is directly applicable to this market. So optical fiber is essentially small cable or a conduit for those of you who aren't too familiar. It can be on the order of around 250 to 500 microns in diameter and is used to transmit very large amounts of data. So this is it's an extremely attractive technology. Specifically, the demand for optical fiber is going to continue to be driven by our increasing needs for more data, internet connectivity, advancements to the next mobile generation, such as 5G, and advancements in next generation technology, such as AI or VR or autonomous vehicles. So in general, optical fiber is going to continue to be a viable technology, and therefore the demand will continue to exist. And while that demand exists, optical fiber manufacturers are continuously looking to reduce their operating costs. Now, to produce optical fiber, there are several processes that are involved, and our focus here today is specifically on the UV equipment that is used in optical fiber to cure the coatings that are applied to the bare glass fiber to give it strength, rigidity, flexibility, that kind of thing. Traditionally, for several decades, optical fiber curing equipment that has been used is what I'd refer to as discharge bulbs, or also called microwave lamps. And the diagram there at the bottom right of your screen illustrates a typical setup for one of these microwave lamps. You have the dotted line there indicating where the fiber is or how the fiber is being drawn in a optical fiber manufacturing plant. It passes through a quartz tube, which I'll refer to as the curing tube, and it's labeled in this diagram as T. Inside that tube is kind of the cure zone. That tube is enclosed in that structure you see there labeled as R. So that's a reflector cavity. That reflector cavity opposes L, which is the lamp or the microwave or the UV source in this setup. So the UV generating source is shining light onto the optical fiber that's being drawn through that curing tube, and the reflector captures any light that is lost or does not hit the target and redirects it back into the curing zone. Now, in recent years, UV LEDs, instead of these microwave lamps, have been proven to be viable alternatives and are starting to emerge in this market. And what makes the UV LEDs attractive is their ability to consume much less energy in comparison to the microwave systems. The microwave lamps also have UV sources or bulbs that could be as large as 15 millimeters in diameter, whereas UV LEDs are in size can typically be, a single chip can be around 1 millimeter squared. Now, for UV LED lamps, they're typically constructed in LED arrays, and that simply means a number of LED rows by a certain number of LED columns put together to create your UV LED lamp. And these arrays actually can also be much larger than even a discharge bulb. So the key takeaway there is whether it's a microwave lamp or an LED lamp, we find that in this application, our UV sources seem to be much larger than the target, which is the fiber that it is being cured. So that leads us to the question that is investigated or looked into in this work is what type of optical designs for UV LED systems can manage photons most efficiently? Or more specifically, how do we maximize the UV in the active curing area while minimizing the energy required to accomplish this, which are both the desirable outcomes from an optical fiber manufacturer standpoint. So to do this, the work that I'm going to be talking about here is summarized. We looked at 4 different UV lamp types. 1 was a microwave lamp, and 3 were commercially available LED systems. For each UV lamp type, we conducted irradiance mapping, which I'll show you in this presentation. We conducted system energy consumption. And then for the LED systems only, since there's several commercially available LED systems out there that are all quite different in optical arrangement, we did optical simulations to get a better idea of what features in these LED systems are contributing to the overall optical performance. All the setups for our measurements or our simulations, we included the quartz curing tube that I described earlier. And finally, once we identified a LED system arrangement or type that looked ideal and optimized, we equipped a high-speed draw tower with this lamp and tested its feasibility in a manufacturing setting. So to jump right in, I'll give a quick summary of what these different system designs look like. So you first have UV lamp type 1, which was a UV discharge bulb or a microwave lamp. It had a 9mm bulb that was enclosed in an elliptical reflector cavity there. So the diagram labels all the reflectors that were used in this. So you have a reflector around the source there, labeled by R. And then you also have a reflector that's opposing the source as the back reflector. And then you can also see there the cross-section of the curing tube T. This UV lamp type 1 was air-cooled via remote blower and exhaust system. The next system we had was UV lamp type 2. Now this was a LED system. What I will refer to going forward is a planar type arrangement. So when I say planar type, it's essentially a multi-row LED array. So this particular lamp type has 7 rows of UV LEDs. It also has a back reflector, you can see there labeled by R, and this system was an air-cooled system. We also had UV lamp type 3, so this was a planar arrangement as well. Instead of 7 rows, like type 2, it had 4 rows. It also had a back reflector, but the other key difference was instead of being air-cooled, this was a liquid-cooled system. And then finally, we have UV lamp type 4. So this was what I'll refer to as a linear arrangement. And by that, I mean a single row of LEDs or a single row LED array. In addition to being a single row of LEDs, this system had 3 separate single rows of LEDs that were fitted with their own focusing reflector optics. And oriented around the curing tube instead of positioned on one side, similar to type 2 or 3. In addition, it also included back reflectors. So there were 3 back reflectors opposing each source there. So you can see the 3 sources labeled by S, the focusing reflector that was paired next to the source labeled by R, and then also the back reflectors opposing each source. And then one final note about this one, this was also, UV lamp type 4 was also air-cooled. So first thing we did was optical simulations. Again, this enabled us to get an idea of what the impact of certain features in the LED lamp specifically, what features were impacting the overall optical performance. So the assumption we made for the optical simulation was that the fiber was essentially a cylindrical cure target. And what this enabled us to do was capture simulation data on the outside surface of this cylinder, in which we could then convert or plot into radar graphs. Now, quick background on how the radar graphs that I'm about to show you work is they have several circular concentric zones, okay? And moving from the inside to the outside portions of the radar graph, it indicates increasing levels of intensity. So if you have data points on our radar plot that occur towards the inner zones, that indicates a lower level of intensity. And if you have data points that are plotted on the outer zones of the radar plot, it indicates higher levels of intensity. Another feature of these radar plots is that it has 360-degree positioning. So if we assume that our target is right there in the center of this bullseye, this enables us to reference where certain features of these different optical designs are located and how they're contributing to the level of intensity that is seen at the target. So the first thing we simulated was a linear system. So a single row of LEDs coupled with the focusing reflector. And the reason we wanted to do this is see what is the impact that the reflector has on the system. So from our radar plot, we see that at position 0, we have the focusing reflector and the linear source. And if we assume again that the target is in the center of that radar plot, the side that is closest, the side of the target that is closest to the focusing reflector and the source appears to have the higher level of intensity. So we take that same plot and then we added a back reflector to the setup. And then again, now we can see that the back reflector is having an impact on the optical performance by increasing the intensity on the target, again, that is located in the center, on the back side of the target now as well. So definitely showing the impact that these reflectors are having on the intensity that is arriving at the target. So with that in mind, we went ahead and simulated our 3 different LED type configurations, starting with UV lamp type 2. So type 2 here, to remind you, is a planar source, 7 rows of LEDs. In the radar plot, the source is at the position 0, and there's a back reflector at the 180 position. So from this, we can see that the higher intensity is on that back side of the target or side closest to the 180 position. Lamp 3 is shown here, and its corresponding radar plot. So we have the source again at the 0 position with the back reflector centered about the 180 position. And similar to lamp type 2, we see that the intensity is much higher on the back side of that fiber. So side closest to the 180 position versus the side closest to the 0 position. And then finally, we had the linear arrangement. So this is, again, the single row of LEDs, 3 separate LED line sources that are positioned around the quartz curing tube. So the source that includes a focusing reflector is positioned at the 0, 120, and 240 position, while at the 60, 180, and 300 position, there is a back reflector. And from this, we can see, again, there's uniformity peak, there's intensity peaking at the 60, 180, 300 position. But more importantly, just comparing the 3 types, we can surmise that type 4 has about an 80% UV uniformity around the target. So if we look at just the type 4 diagram, we see that we have data points consistently plotted within or even above the 80% UV intensity band in this chart. So that's what's indicating the 80% uniformity. In comparison, type 2 and 3, we can see that it ranges between 50 to 60% uniformity consistently around the target. So definitely a difference in uniformity among the 3 types. So moving on, we went ahead and did our radiance mapping. So to do the radiance mapping, essentially a customized tool was developed in-house. And this tool enabled us to determine the distribution of UV light intensity within that curing tube. So without going into too much detail about this test setup, you can see the picture of it here in the bottom left of your screen. What this test setup includes is an optical probe that is coupled to a photodiode detector that can capture the relative optical signal. So if I zoomed in there, you have the quartz tube at the bottom of that picture. That optical probe basically is inserted into that tube and translates across the cross-sectional area of that tube, plotting out and capturing data points of relative UV intensity. So we did this for each lamp, and each lamp type was mapped at its maximum operating power. So to quickly give a preview as to what this looks like, we did it with UV lamp type 1. So if you recall, UV lamp type 1 is our microwave broadband system And now when I say broadband, UV lamp type 1 emits wavelengths from 200 to 600 nanometers. And this is important as we go forward to look at the different maps, because UV lamp type 1 compared to the other LED lamps has a broader range of emitting wavelengths. Types 2, 3, and 4, which you'll see on the next slide, only emit at 395. So what this means for our plot is that the types 2, 3, and 4 are normalized to itself as they're emitting relative intensity at a single wavelength, versus UV lamp type 1 is emitting intensities at several wavelengths, and it was not filtered out in this study. So they are showing different things, but in general, we can at least get an idea of the distribution of light within that curing tube. So the curing tube in that radar in the radiance map we see here is outlined by that white dotted line indicating the perimeter of the curing tube. The darker oranges and reds in this map show that there are higher levels of intensity towards the center there. And as we move to the greens and the yellows and the blues, indicates lower levels of relative intensity. So looking at our LED lamps, we have UV lamp type 2, UV lamp type 3, and UV lamp type 4. And these are the 3 LED lamps that were looked at in this study. So some key takeaways from looking at these 3 maps. The UV uniformity at the target is different among the 3, with type 4 having the highest relative intensity, and type 3 having the lowest measurable UV intensity. The other thing to note is the uniformity. So we can see kind of the contour of the distribution in the different types. The uniformity again seems to be highest with type 4, with and then lowest with type 3. If we're just comparing the relative scales, we can also see that UV lamp type 4 has 4 times higher relative peak intensity in comparison to 2 and 3. So with that, we then continue to operate the systems at their maximum operating power and measure their individual power consumption. So for type 3, if you recall, was liquid cooled, so we needed to include the chiller in this measurement. Type 1, we did not include the blower system, but that can typically consume about 1 kilowatt of power. Below in the table, you can see the results of our energy consumption. So few major takeaways is that, number one, LED systems versus microwave systems, there is a huge energy saving. So type 2 through 4, whatever system you choose, you're having a huge amount of energy savings. You could have as much as from this measurement, it looks as much as 80% less energy consumption per lamp. When you compare LED versus LED, though, they're comparable in energy consumption, but they achieve different levels of optical performance from what we saw. So essentially, UV lamp type 4 has the lowest energy consumption, but offers the highest UV intensity plus highest highest UV uniformity. So taking that piece of information, we identified that as the optimized setup. We equipped a high draw speed tower. And when I say high draw speed, these are optical fiber draw towers that can achieve speeds above 3,000 meters per minute. So for this study, it was done at 3,400 meters per minute. We equipped this tower with UV lamp type 4, and we collected cure data on coating that was applied to the optical fiber. And for this study, we used an LED-specific formulation. The summary of our test is captured in some of these data points on the table and on the screen. We can see with as few as 4 LED lamps, we were able to pass some preliminary cure specifications. And this is relevant because at these speeds, typically previous work has shown you need at least 8 lamps to do this. Furthermore, this also demonstrates that it's feasible to meet a cure spec at high draw speeds with an all LED line, and you can consume less than 4.5 kilowatts per line for the curing process. So very interesting and attractive way, I'm sure, moving forward for optical fiber manufacturers to utilize this kind of setup. So some quick conclusions here. UV lamp type 4 seem to place more of the photons in the active curing area where it can be utilized compared to some of the other UV LED lamps. So the other UV LED lamps appeared to use the same or comparable amount of energy, but did not deliver the UV to the usable area like UV lamp type 4 did. External optics, like the reflectors, as shown in the simulation, can play an important role in improving the intensity of UV arriving at the cure target. An optimized linear optical arrangement can provide high uniformity, high intensity, and low power consumption. And positive cure results can be achieved by these type of linear optical arrangements, specifically even on high draw tower speeds, which is almost an extreme case situation. So with that, I conclude my presentation and open the floor for any questions. Thank you.